Closure type inference and annotation. Closures don't require you to annotate the types of the parameters or the return values like functions do. Type annotations are required on functions because they're part of an explicit interface exposed to your users. Defining this interface rigidly is important for ensuring that everyone agrees on what types of values a function uses and returns. But closures aren't used in an exposed interface like this. They're stored in variables and used without naming them and exposing them to the users of our library. Okay. Type annotations, U32. Oh. Ooh. So what they're bringing up here, something I forgot to mention and didn't even notice, was in this closure, we have expensive closure, right? We passed in number. That number is not, there's no type annotation associated with it. We don't know if it's a U32. We don't know if it's even a number. It could be a string for all we know. However, the thing to notice is that we do not have to put the type annotation. And the reason they say we don't have to put the type annotation is because closures aren't exposed to our users. That's important because if something was exposed to our users, then our users can use it and we can use it. As such, we need to be explicit as to how they can use whatever item this is, whether it be a function, whether it be a struct. But closures, we don't give them the use. Closures just for us. And seemingly because they're just for us, we could not do this? Okay. Closures are usually short and relevant only within a narrow context rather than in any arbitrary scenario. Within these limited contexts, the compiler is reliably able to infer the types of the parameters and the return type, similar to how it's able to infer the types of most variables. Making programmers annotate the types in these small anonymous functions would be annoying and largely redundant with the information the compiler rarely has available. As with variables, we can add type annotations if we want to increase explicitness and clarity at the cost of being more robust than is strictly necessary. Annotating the types for the closures we define in listing 13-5 would look like the definition shown in listing 13-7. Okay, so I understand it now. So in closures, yes, we don't have to annotate the type. The reason why we don't have to annotate the type is because it's kind of redundant. Given the context in which we use closures, which is very small, seemingly, the compiler usually can figure out what the types are going to be. Just like when we define variables, we don't necessarily have to declare the type explicitly. The compiler can figure it out from the context it has and do it for us. It is the same thing with closures. However, if you want to explicitly write the type annotation, you can, and they show that in this listing, where we do num, colon, and then U32. And then we also have the return type, which is U32. So we have that option. Let's look what it looks like currently. Currently, we don't even say if anything's being returned. Wow. Yeah, I can see how this can be confusing. Okay. So yeah, if you want to be explicit, by all means be explicit. You don't have to. They give you that option, but yeah, it's up to you. With type annotation added, the syntax of closure looks more similar to the syntax of functions. The following is a vertical comparison of the syntax for the definition of a function that adds 1 to its parameter and a closure that has the same behavior. We've added some spaces to line up the relevant parts. This illustrates how closure syntax is similar to function syntax except for the use of pipes and the amount of syntax that is optional. Alright, so they have an example of a function. This function adds 1 to whatever thing you pass in, so x, and then returns x plus 1. And here is how you write it if you want to be explicit in terms of your anonymous function. You have your pipes, you have your x, and then they define the type, they define the return type, and they did x plus 1. Here's another way of writing it, which is similar to what we did in our example, which is we have the pipes, x, no type, and we don't say anything's being returned. Something is being returned, but we don't explicitly state that. And we do x plus 1. And then lastly, because we can do it, we can, the curly braces for the body is optional if it's just one line. We can write x, and they did the spaces here just to keep it lined up, but x plus 1, and then semicolon, and return that. The first line shows a function definition, and the second line shows a fully annotated closure definition. The third line removes the type annotations from the closure definition, and the fourth line removes the brackets, which are optional because the closure body has only one expression. These are all valid definitions that will produce the same behavior when they're called. Closure definitions will have one concrete type inferred for each of their parameters and for their return value. For instance, enlisting 13-8 shows the definition of a short closure that just returns the value it received as a parameter. This closure isn't very useful except for the purpose of this example. Note that we haven't added any type annotations to the definition. If we then try to call the closure twice using a string as an argument the first time and a U32 the second time, we'll get an error. So here's what they're demonstrating. So here's the closure. It takes an x in and returns an x out. There is no type annotation, so it can be string, it can be an integer, it can be whatever it wants to be. However, in the example, if we first call it with a string, we know, oh, it's supposed to be a string. If we then try to call it with a integer, we get an error. And the error is mismatched types. They expected it to be a string, and they found an integer instead. So what does this tell us? This tells us that when we write a closure, even though we're not writing the type annotations, the compiler seemingly infers the type from the first call we make with the closure. So in the first call, we said it was supposed to be a string, and we said we're supposed to be returning a string. Okay. So it knows that. The compiler says you're supposed to be taking in a string and returning a string. We then give it an integer and it yells at us for not giving us a string. For us not giving them a string. The first time we call example closure with the string value, the compiler infers the type of x and the return type of the closure to be a string. Those types are then locked into the closure in example closure, and we get a type error if we try to use a different type with the same closure. Understood? Storing closures using generic parameters and the function traits. Let's return to our workout generation app. In listing 13-6, our code was still calling the expensive calculation closure more times than it needed to. One option to solve this issue is to save the result of the expensive closure in a variable for reuse and use the variable in each place we need the result, instead of calling the closure again. However, this method could result in a lot of repeated code. One option to solve the issue is to save the result of the expensive closure in a variable for reuse and use the variable in each place we need the result, instead of calling the closure again. However, this method could result in a lot of repeated code. Fortunately, another solution is available to us. We can create a struct that will hold the closure and the resulting value of calling the closure. The struct will execute the closure only if we need the resulting value, and it will cast the resulting value so the rest of our code doesn't have to be responsible for saving and reusing the result. You may know this pattern as memoization or lazy evaluation. I can never say that word, but yeah. Lazy evaluation is another way of saying it. So let's go over this, at least these two paragraphs. So here they reiterate the problem, which is our code is calling the expensive calculation closure more times than it needs to. And they say yes, we can store the result of the expensive closure in a variable and then use that as we need it. That is an option. But they said the downside to that option is that it has a lot of repeated code. And then they introduce a new option using lazy evaluation. More or less, what we're going to do is we're going to put this closure within a struct. And when we run the closure, we're going to run the closure when we need the value. And then we're going to store that value so that if we need this closure again, instead of running it again, we just return the stored value. And this is lazy evaluation. Lazy evaluation meaning seemingly when we call it when we need it. If we don't need it, we don't call it. And if we need it multiple times, instead of calling it multiple times, we return the previous result that we had. To make a struct that holds a closure, we need to specify the type of the closure, because a struct definition needs to know the types of each of its fields. Each closure instance has its own unique anonymous type. That is, even if two closures have the same signature, their types are still considered different. To define structs, enums, or function parameters that use closures, we use generics and trait bounds, as we discussed in chapter 10. The function traits are provided by the standard library. All closures implement at least one of the traits: function, function mutable, or function once. We'll discuss the difference between these traits in the capturing the environment with closures section. In this example, we can use the function trait. We add types to the function trait bound to represent the types of the parameters and return values the closure must have to match this trait bound. In this case, our closure has a parameter of type U32 and returns a U32. So the trait bound we specify is function U32, return type U32. Okay, let's go over this a little bit from here to here. So we already know that what we're going to do, which is we're going to create a struct. This struct is going to take in a closure and then use lazy evaluation, which we already described. However, what they're stating here is that functions and structs need to know what parameters they're taking in. So you need to have the type annotations, which can be tricky when it comes to anonymous functions because each anonymous function has a unique type. So even if two closures have the same signature, they do not have the same type, and as such, they cannot be passed in the same functions or structs. So in order to avoid that, what we're going to do is we're going to use traits to define how we're going to pass these anonymous functions into our struct/functions. And the traits that they're talking about are the traits provided by the standard library. We have function, function mutable, and function once, which they haven't gone over yet, but it kind of seems like function mutable allows you to mutate something. Function is just a generic, takes in, returns. And then function once is a function that only happens once. I don't know. They'll explain it later on in the capturing environment with closure section. So moving onward. In listing 13-9, show the definition of the Castor struct that holds a closure and an optional result value. So here we go. We have our struct, Castor. It caches. It has a generic of type T, okay, where T is the anonymous function. It has the anonymous function, and the function is takes U32 and returns U32. Then it has the calculation, which is T, and it has the value, which is the option U32. Understood. So that makes sense. Struct takes an anonymous function. The anonymous function is equal to the calculation, so that can be called there, and the value is probably where we're going to store it. The Castor struct has a calculation field of the generic type T. The trait bounds on T specify that it's a closure by using the function trait. Any closure we want to store in the calculation field must have one U32 parameter specified within the parentheses after function, and must return a U32 as specified after the error. Note, functions can implement all three of the function traits too. If what we want to do doesn't require capturing a value from the environment, we can use a function rather than a closure where we need something that implements an function trait. meh. So this note is stating that yes, we're using function traits. Yes, in this case, function traits sort of imply that we're using an anonymous function, but functions can also satisfy these traits as well, and we should keep that in mind. The value field is of type option 32, U32. Before we execute the closure, value will be none. When code using a Castor asks for the result of the closure, the Castor will execute the closure at the time and store the result within a sum variant in the value field. Then, if the code asks for the result of the closure again, instead of executing the closure again, the Castor will return the result held in some variant. The logic around the value field we've just described is defined in listing 13-10. Alright, so here's the meat of everything. What they're saying here is that the value field is going to store the value of the closure, and when somebody asks the Castor for the closure, if Castor has a value, it's going to return the value. If it doesn't have the value, it's going to evaluate it and then post-evaluation return the value, and also store the value so that if it's asked again, it can just return the value without doing the evaluation again. And now here is where they have that logic. So this is what I want to see. So you can calculate a new one, or this is like the helper, right? New calculation, new Castor, pass in T, calculation, value equals none. Makes sense? Return an instance of this struct. And then we have the value, which is going to be a function call, mutable self, has the argument U32, and returns U32. Match. Self.value. If value has something in it, then we return the value. If value has nothing in it, then we do the calculation with the argument and return the value. Though this is going to do what we want, I am not sure about this part. So one reason why this is awkward for me is this takes in an argument. This argument may change. If the argument changes and this still has a value in it from a previous run, then it doesn't sound like the value in the sum changes at all, because sum is already defined. But outside of that, this is doing exactly what we want for this scenario. So let's write this up and continue onward. So going up here so I can write it the first time. Hold on. Here we go. So let's get this struct. Struct Castor T, and I can do a tab where T function U32 returns a U32, and then we have our calculation, which is equal to our closure, and we have our value, which is equal to our option, and the option has the innards of U32. Okay, and then continuing onward, we have the implementation block. So implementation block, the Castor. Takes generic T, put a space just like you guys did. Signature of the Castor. Where T, looks like I have to write this twice. U32 returns a U32, and now we have the what's called like auxiliary function. I forgot the explicit name of this, but it creates a new instance of Castor. Function new, and takes in a calculation T, and it returns Castor T, and it's really just Castor calculation, and value is going to be equal to none. Comma, which makes sense. And for the next function, we have value, which is going to take a mutable reference to self, because it can change self. You could change the value of one of the parameters within itself, like value could change, can be updated. And then we have the argument. It's going to be u32. Returns u32. And then we have our match statement. Match self.value. And we have our first arm, which is going to be sum v. And if that does exist, then we're going to return v. And if it is a none, let v equal to, this syntax looks a little weird to me. Has it in parentheses, self.calculation, and then we're passing in the argument. And now we're storing that value, self.value equals sum v. And we'll return v. That makes sense. And that's the end of the second arm. Okay, so let's look at this one more time just to be clear on exactly what it's doing. We have our struct with our Castor. Takes in generic type T. Generic type T has the bounds of function, so it's going to act like a function where it takes in a u32 and return to u32. In terms of parameters, we have calculation, which is going to be equal to our anonymous function that we're passing in, and we have the value, which is going to store the result of the anonymous function. Down in the implementation block, we have the new function, which is going to create an instance of our Castor that just takes in the anonymous function, saves it as calculation, and sets the value to none. And then we have another function called value, which takes a mutatable version of self because it can update the self.value. But in any way, the argument takes a u32, returns to u32, and it has a match statement on the self.value parameter. Parameter. No, property. There we go. Property. Self.value, we check to see if the value is equal to sum v or is none. If the values of, if self.value is equal to sum v, as in this has a value to it, then we return that, which is the cast value. If it's equal to none, then we call the calculation, we wait for the result, and then we store that result and return that result. We want Castor to manage the struct fields values rather than letting the calling code potentially change the values in these fields directly. So these fields are private. So here, what they're saying in this short paragraph is that we want the struct to manage these fields instead of allowing the function caller, and I guess the programmer writing the function, to manage them for us. Just for like security purposes, more or less, keep everything nice and tight. And as such, we made these private. So the only person, thing, or object that can modify these two fields is the struct itself. The Castor new function takes a generic parameter t, which we define as having the same trait bound as the Castor struct. Then Castor new returns a Castor instance that holds the closure specified in the calculation field and a none value in the value field, because we haven't executed the closure yet. So right there, they just described the new function, how it works. Take in the anonymous function, store it as calculation, set value equal to none. Cool. When the calling code needs the result of evaluating the closure, instead of calling the closure directly, it will call the value method. This method checks whether we have a resulting value in self.value in a sum. If we do, it returns the value within the sum without executing the closure again. So going back to this value, this v is just a placeholder for the value of self.value. So as long as self.value exists and it has some value that is a U32, then we return that. If self.value is none, the code calls the closure stored in self.calculation, saves the result in self.value for future use, and returns the value as well. So right there, it's just talking about this arm. If self.value is equal to none, then we call the calculation function with the argument, and we store that value as self.value, and we also return it. Listing 13-11 shows how we can use this Castor struct in the function generate workout from listing 13-6. Alright, so what did they change here? We have generate workout, we have intensity, we have a random number, same. Let mutable expensive result equal Castor new number, calculating slowly, thread sleep, return number. Oh, yeah, that makes sense. So yeah, Castor new takes in the anonymous function, and this is the anonymous function. I see. So this is our T, and then we just call it the way we've been calling everything else. But we add a value because that is the method we're calling on Castor. So this is an instance of Castor now, right? And we call the method value with intensity. And if the intensity has never been called before, then we're in this scenario where value is equal to none. And then we're going to calculate it and then store the value. In this case right here, intensity value has already been called once, so value should already be stored because of the previous call cast it, and then we're just returning it without waiting. And then here, we've never really gotten to this case, but it just calls it once, waits 2 seconds. All right, so let's write that out, and then we can test it just to make sure it's doing what we expect. And the way we can verify it is we can call our generate workout the way we have been calling it, and then make sure this waits for 2 seconds instead of 4 seconds, because this goes through the calls twice. So let's write this. So we have the closure here, and what we're doing is we're adding our Castor new, and we're encapsulating our closure. Encapsulating as in like putting all that information from the closure within the function called to new, not the programming definition of encapsulate, just like physical definition of we're putting something in something else. And this is called expensive closure. They changed the name back to expensive result, and they made it mutable because it can change itself, so it has to be mutable. Because it can change the value of self.value for Castor, thus it has to be mutable. So make that result and make that mutable, and then we can update these. Result.value result.value and result.value. And if all works well, then this should just work as expected. Run it. Let's do our counting. 1, 2, 3. Yeah, it was less than 4 seconds. I may count a little fast. But yeah, those came out right after each other. And there is no calculating slowly because we didn't call the expensive call, this thing, twice. We only called it once. I may have skipped over that really quickly. So one way we can see that we only call the expensive function call once is because calculating slowly only happened once. that happened when we first called the expensive result. The second time, we just took the cast value and used that. As such, we only see calculated slowly once in the output instead of twice. Cool. So moving onward. Instead of saving the closure in a variable directly, we save a new instance of Castor that holds the closure. Then, in each place we want the result, we call the value method on the Castor instance. We can call the value method as many times as we want, or not call it at all, and the expensive calculation will be run a maximum of once. Try running this program with the main function from listing 13-2. Change the values in the simulate user specified value and simulate random number variables to verify that in all the cases in the various if and else blocks, calculating slowly appears only once and only when needed. The Castor takes care of the logic necessary for ensuring we aren't calling the expensive calculation more than we need to, so generate workout can focus on the business logic. Okay, that was a mouthful, but more or less they want us to run the program with different inputs to verify that all of the if and else blocks within here work as expected, and that we only see calculate slowly once, a maximum of once. Because if it needs to be called, this is expensive function. If it needs to be called, it should be called, but it should only be called once, and thus we should only see this once in every output, with the exception of when it's not called, of course. So how do we do that? Let's make this big so we can see everywhere. We already did one case where we got 10 push-ups, 10 sit-ups. That's this if block. So now we need to check the second, the else block, this section. And we have two cases in here. We have the case where random numbers equal to 3. We don't call the expensive output. And then we have the other case where random number is not equal to 3, and we call the expensive output and we make that person run. Sorry for you. So let's try that out. You need a number greater than 25, or 25 or greater. Make that 25, and let's make this person run for 18 minutes. They're a runner. They're good at this. They're not going to die. Calculating slowly. Ooh, they have to run for 25 minutes. My bad. The random number only calculates whether or not they need to take a break, whether or not we give them a break. It is this value that specifies how many minutes they're going to do something. And this person is going to run for 25 minutes. My bad. To compensate, let's give you a break. And this should happen immediately because it does not call the expensive closure. So yeah, take a break today. Remember to stay hydrated. Make this small again. Cool.